Hi everyone, my name is Feng Xiao from Georgia Tech. So this is not only my work, but also the work of my wonderful co-authors from Georgia Tech and Texas A&M. So today I'm going to talk about some interesting new attack in Node.js ecosystems. Before the talk normally begins, please let me introduce myself a little more. So I'm a CSD PhD student at Georgia Tech, and I'm a vulnerability researcher. My research is about building tools to automatically detect and exploit zero days, so that people can be aware of both the existence and the consequence of their security bugs. So I do research in web application security, but I'm also enjoying researching security problems in other areas such as software-defined networks and x86 virtualizations. Okay, so these are the topics I'm going to cover today. The talk will be divided into three parts. First, I will introduce the technical details of the new security risks we discovered and discuss how to exploit it. And then we will talk more about the bug finding part, which is about the lessons and insights from building such JavaScript security analysis tools. And in the end, we will give up impact analysis of our discovered vulnerabilities and have some evaluation data on our new tools. So first of all, please let's take a quick look at the new vulnerabilities we found. In total, we found 13 zero-day vulnerabilities from widely used programs. Many of them have more than 1 million of downloads, such as MongoDB official drivers, class validators, and so on. So these bugs can be exploited to launch serious attack effects, such as leaking credential user data, bypassing security checks, and denial of services. Yeah, so this is pretty much the big picture of our research. Okay, so before we touch the technical detail, let's have some little background about the Node.js. Node.js is used for executing JavaScript outside of browsers. The picture on the right is the overall system design of the Node.js. To interpret and execute JavaScript, the Node.js implements a runtime execution engine on top of Chrome EV8 to satisfy the needs of server-side scenarios. The runtime also provides a set of APIs to let JavaScript interact with the host environment. With the provided APIs, the JavaScript code can access the host environments like any other server-side languages. For example, they can read and write file systems or execute system command. So Node.js is pretty powerful. Nowadays, many websites are deployed in Node.js. For example, Node.js are intensively used in companies like LinkedIn and PayPal. And also, we are using a lot of Electron apps. And such Electron apps are also powered by Node.js runtimes. Web-based applications are the most common types of Node.js programs. For these web-based applications, packing the communication data into object representation is really common. So this feature is convenient and very powerful. With the help of this feature, Node.js applications can send or receive very complex data structures. From monthly downloads statistics on the right, we can have a sense of how object sharing is being supported and used by the Node.js ecosystems. So the diagram demonstrates how the object sharing is being used. In Node.js ecosystem, there are two major methods of serializing communication objects, which is the query stream-based sharing and the JSON-based sharing. As shown in the picture, if the user wants to update the age information in his website, he may do this in two ways. First, he can send his data through the standard query string in the URL. And also, he can send a JSON string to the server in somewhere such as the post body. Upon receiving the request, the Node.js server will pass the request and pass the data into an object. So the object can further propagate into the corresponding logics in the program. Okay, so this is basically how Node.js object sharing is carried out. Usually, if we want to evaluate the security of such a program, we may inject a different payloads into the H field to trigger potential vulnerabilities, such as cycle injection or cross-site scripts. But what if we choose not to test the existing data fields? Since we can pass an object into the server, what will happen if we inject additional properties into the program which is not expected by the server program? In particular, if an attacker can send properties that forge or override certain internal states, the attacker may easily obtain dangerous abilities such as manipulating the key logics of the program. So what we are going to introduce is the hidden property abusing, which we call HPA. HPA leveraged the object sharing in Node.js to forge or tamper critical program states in the Node.js applications. We called these additional properties we injected as hidden property because these properties are kind of like some hidden parameters valid to the endpoint user API. These parameters are associated with certain internal states. However, nobody knows their existence until an attacker finds it and exploits it to tamper internal states. In this talk, we mainly focus on the server-side scenarios, where a remote attacker wants to hack a Node.js web application or some microservices. To exploit the vulnerabilities, the attacker accesses the legitimate interface, such as the web endpoint, to send his payload. In most cases, the payload should be in the plain objects, which is the simplest object representations, which only support the primitive types. We have these restrictions because the plain object types is the most widely supported object types in Node.js object sharing. Okay, so during our research, we discovered two types of attack vectors. We call the first one as app-specific attribute manipulation. This one is for manipulating certain internal property defined by the application themselves. Such internal properties are supposed to be initialized and managed by some internal functions, and they usually represent certain internal states of the programs. As shown in the picture, the init role is an internal function that are responsible for managing the access right of the user object. However, with HPA, attackers can propagate a conflicting name property into the user object, and thus control the internal states. As shown in the program also provided an API called update in external usage. If a malicious user injected his payload, which is an additional key value pair, into his request, then the additional key value pair probably will overwrite the existing data on the user object. So this attack vector is really useful when we want to abuse certain concrete logics in large programs, such as order states or user privilege management. Also, HPA can also target at some unique JavaScript schemes, such as prototyping. We call the second attack scenario as prototype inheritance hijacking. In JavaScript, every object has a link to a prototype object. When the JavaScript code wants to access a property of an object, the property will not only be searched within the object itself, but also the prototype of the object and even the prototype of the prototype, until a property with a matching name is found. As shown in the picture, when the JavaScript code wants to access the constructor property from the input object, it will first search locally within the input object. Since there is no properly named constructor there, the code will continue its search to its prototype, where the constructor is really located. With HPA, we can hijack the inheritance chains and forge our own payload as our internal properties on the chain. As shown in the picture, if we inject a property named constructor, the searching process will be really different. Since there is already a property named constructor within the input object, the search will immediately stop and end up returning a user-controlled value. As demonstrated by the red circle here, the value of the constructor will become the string Rick and Morty rather than a normal JavaScript prototype function. So the second attack vector is very useful because we found many JavaScript developers tend to trust the properties inherited from prototypes, and they also make many security-sensitive decisions based on them. Also, we should be aware of the differences between the prototype pollution and the prototype inheritance hijacking. So, prototype pollution, as the name suggested, is about attacking and tampering the prototype objects. However, our attack vectors does not modify the object, the prototype object. So the root cause of HPA is that the Node.js fails to isolate the unsafe objects such as user input from critical internal states. To make a clear demonstration, the HPA can be seen as a new security risk under the weakness category 915, whose child variants are all about improper modification of dynamic objects. As shown in the hierarchy tree on the right, there are some similar issues on the other language platforms such as Ruby mass assignment and PHP object injections. Although these variants share the same behavior feature dominated by 915, they all have their own patterns due to the language differences. For example, the Ruby mass assignment is a set of vulnerabilities discussed in widely used Ruby web framework called Ruby on Rails. Unlike HPA, the attacker does not pass objects into the Ruby program. Instead, the attacker abused a framework-specific assignment feature to tamper the existing object that associate with the assignment. So the payloads are also different. The mass assigned payloads are literal values. However, HPA can introduce both hidden properties with either literal values or nested objects. More importantly, Ruby is strongly typed, so the mass assignment vulnerabilities cannot introduce new properties into the victim object. However, HPA can inject arbitrary properties, which make HPA very flexible and powerful. Okay, with several pages of concept introduction, I think it's time we can hack some real targets. In this example, we target as our popular web framework named Routing Controller. We will hack its official code to demonstrate an end-to-end attack from security check bypassing to database injection. The figure on the right can give you a brief idea on how our example works. In this example, a server program is deployed using routing controllers. If a remote user wants to authenticate with the server, his data will flow into the following components. First, he will send his serialized data into the web API endpoint. Upon receiving the request, the authentication module will instantiate an object according to his JSON string and send it to the Para handler. Here we use the green box to demonstrate the user input object, and we use the handler will first collect the internal format specifications, which is the blue box here, and he will merge the internal format specification with the input object and invoke the input validation API. So the input validation components will synchronize the user input data according to the format specification. In this case, it will check if the email field is legitimate or not. If the check pass, the user object will flow into the database. Okay, so this is overall data flow. Let's analyze how we can attack the logic step by steps. The first step is the hidden property injections, where the malicious user includes an additional property into the request, which is the constructor in this case. As shown in the picture, when the server program instantiate the user input, there will be an additional property within the param object, which is the constructor. And in the second step, the program will prepare the parameters needed by the input validation API. The server program will merge the user input with the param, which is the param, with object named schema. So the merging operation is performed by putting every properties of the param objects into the schema object. So this is a process very much like object assign. To simplify the demonstration, here let's just use object assign in this example. By performing the merging operations, the hidden property constructor also transformed into the schema. So by performing such a transformation, we now can hijack the inheritance chains of the constructor on the schema object, like we have demonstrated in the second attack vectors. Actually, the constructor schema plays a very important role in the routing controller. As shown in the picture, the schema object follows an object-oriented program style, which uses the constructor of his prototype to store important format restrictions. Okay, so as a result, the merging operation enables us to hijack the inheritance of these important format restrictions. As shown in the picture, when the constructor is read by the getGamma function, our hidden property will immediately matched and return to the code. To bypass the input validation, we just need to set the format specification as an invalid value, so our cycle injection payload can escape the check. The last step is much more straightforward. The validated payload then flows into the sensitive database API to finish the entire attack. So this is how the entire HPA exploit can work. Actually, the code logics behind vulnerabilities is much more complex than the simplified graph here. For example, the input validation module itself contains more than 30,000 lines of code. So it would be really helpful if we can have a tool to help us automatically track all these data structures and automatically detect all these hidden properties and even automatically exploit them. So what is the challenge of building such a tool? First of all, this is JavaScript. Analyzing JavaScript is known to be hard due to the dynamic feature. The fact is, even if we have chosen a reliable analyze framework as our underlying platform, and we design smart methods, and we test a large number of programs, we still occasionally encounter crashes and incompatibilities issues when trying to analyzing large and very complex programs. And the second challenge is, does HPA actually create new data dependencies? But the program analysis is good at digging the existing data flows rather than creating new ones. Third, from our running examples, we can observe that HPA actually exploit internal program states. So the attack effect highly depends on the code context. This makes the detection more challenging. Okay? So to overcome these challenges, we design and implement Lynx, a hybrid JavaScript program analyze tool to detect and exploit HPA vulnerabilities. The Lynx is a type of wildcat, and in Greek myths, it is believed that the Lynx can see other people's can't, and his role is for revealing the hidden truths. So in our system, it's for revealing the hidden properties. The picture below gives a high-level workflow of Lynx. The tool mainly consists of two parts. The left part is for discovering the potential hidden properties, which is the core components in our system. It will first leverage data dynamic flow analysis to track the user input data flows. And then it uses static syntax analysis to infer potential hidden properties. The right part is about how we can detecting the harmful hidden properties from all those potential candidates and generate exploit for them. So to help future Node.js security research, we will open source our Lynx project on the GitHub link at the bottom. So the very first thing links will do is dynamic flow tracking. First of all, links will generate a label object, which is a unique key and value pair. Links will inject the label into the input data of the program. Different properties from the input objects may flow into the different program logics. So to track all the potential propagations, our label injection is performed recursively. Taking the routing controller cases as an example, as shown in the left part of the picture, links will first generate 3 different input objects by label injecting the original one. In each time, link will inject the label into a different property, such as the such as the email and the password, and also he will inject the label into the root of the input object. And then we execute the mutated test input in our instrumented framework. To observe the program execution, we leverage a JavaScript analyze framework called Jalanki to instrument our test program. Since we are studying the data flows, we instrument only the variable read and write and object property indexing and the function calls. Then we execute the program. During the execution, links will examine every object within the data flow. If an object carrier carries our property labels, we will record it for further analysis, and we will code the objects that carry the labels as property carriers. So now we have a list of property carriers recorded that an object is flagged as a property carrier because we detected our injected label under his body. So if we can propagate our label here, is it possible we also propagate other properties here? More specifically, if we propagated a property with a conflicting name with certain internal properties, we may be able to overwrite the original states. So we need to extract all the original properties under the carrier. So now we want to extract all the childs from the property carrier and flag them as hidden property candidates. To achieve this goal, we need static syntax analyze to extract necessary syntactic information from the code. So the picture on the right demonstrates how we parse a statement from our running example. So to parse this statement, links will traverse the syntax tree until reaching the property carrier, which is circled by the red line in our graph. Then it records all the properties under the carrier. In our case, the hidden property candidate is the constructor. Okay, so this is the output screenshot of the first component. As you can observe, the links will first instrument the code base. And in total, you can observe that we tracked 43 different carriers. And as indicated by the red circle, links successfully detected a hidden property named constructor. So in the previous components, we discovered the key name of the potential hidden properties, which is the constructor. By injecting a property with such a key, we may override the certain internal states. However, we still don't know whether the candidates can be override or not. And we also don't know how to introduce attack effects with these candidates. So apparently, links should do more. Let's revisit our running example to see if there's any insights to guide us design such exploitation components. So the feature on the right, on the left, is the vulnerable code from our running example. As we have discussed many times, HPA exploit internal program states, which means its exploitation highly rely on the code context. So it is important that we can conclude a set of sensitive behaviors. These behaviors should clearly indicate certain security consequences by themselves, so that we can decouple the harmfulness detection from the code context. Also, from this running example, the exploitation is mainly about manipulating the return result. For example, there are two possible paths in this picture. If the execution enter the branch on line 19, we will get a validation failed, which is what we don't want to see. But if we go into line 21, we can successfully pass the check. So the exploitation point and the override point may not be the same place, which means we should not stop our analyze at line 11. And we should continue exploring all the possible paths that can trigger by the manipulating the hidden property. We studied and concluded 6 general types of sensitive sinks. The first type is keyword-based sinks, such as C1, C2, and I1. Based on our observations, certain parameters of sensitive methods are really a common attack targets for HPA. Hence, we collect widely used API that are frequently involved in handling user input, such as file system operations, database queries, APIs, like that. And we made our best effort to collect as many sensitive APIs as possible. While we know that it is not complete, but it can be easily extended over time. The second sink belongs to the behavior-based sink. For example, in the sink I2, we are monitoring that whether our hidden property can change the return value of the module. Such sinks are killing weapons for security-related modules like input validators. Okay, after defining our sensitive behaviors, we want the hidden property to trigger as many as possible branches and monitor whether we can hit a certain sink. To achieve this goal, we will use symbolic execution to explore the hidden property value space. So the links first generate an exploit template that can reach the potential vulnerable properties. We denote such structure as a template because links actually does not inject concrete value here. Instead, he will inject a placeholder, which is used by the symbolic execution. Then we will run the test program on with our constructed templates and symbolically executing the hidden property. So as shown in the picture, with the symbolic execution will explore all the path constraints on the path. And if the exploration hit a certain sink, we will fetch the corresponding payloads that can trick the sink. So this is the output of our the exploit module. From the circled area, we can observe that the key value pair, constructor and 1 trigger the sink I2. And in the last line, we can find that links automatically generates exploits that can successfully lead to the input validation bypass. So here, let's have some evaluation data and have more insights about the impact of our research. So during our research, we choose 60 widely used programs from NPM. There are 55 modules and 5 web applications. With help of links, we tracked more than 1,030 carriers and detected 300 hidden properties candidates associated with them. In the end, we confirmed 13 zero-day vulnerabilities. And with the help of symbolic execution, links even synthesized 10 exploits. So how is the impact of the detected vulnerabilities? We found that the HPA can introduce various attack effects, such as leaking the credential data, bypassing security checks, and denial of services. Based on the impact analysis, we can observe that HPA compromised previously unreachable program states, which effectively enlarged the attack surface. Also, we could notice that HPA is not a simple input validation problems. And also many input validators themselves are vulnerable to HPA. Okay, so in the following slides, I will pick up some interesting vulnerabilities from our result and case studying how we leverage HPA to compromise them. And note that all the vulnerabilities here have been reported to the vendors. So the first case comes from MongoDB official driver. We found that we can temper an internal state named Bison type. So a background here is that the MongoDB leveraged this Bison type to indicate the data type of the query object. However, when serializing the query object, MongoDB will ignore the object with an unknown Bison type. So what if we abuse the logic in a query condition object? The code on the right is an open source online game. The online game used the vulnerable MongoDB API to implement his user management logics. As shown in the picture, there are two APIs implemented by the online games. The first one is about loading a user, and the second one is about delete a user. So as an attacker, by injecting an unknown Bison type, such as Black Hat, into the user input, the attacker can force the MongoDB not serializing the query condition. So the MongoDB will always return the first user on the MongoDB database. With this ability, the attacker can log in or delete arbitrary users in the database. And so the second case is from another widely used in-memory JavaScript database. The hidden property is more like a backdoor, which helps attacker access the sensitive data. So in TuffyDB, we discover a hidden property named ID, which is an internal index for the database items. Once we specify our own ID in the query, TuffyDB will ignore other query conditions and directly return the results associated with the index. Moreover, since the internal index is in an easily guessable format, such as T00002R, so that attacker can use these vulnerabilities to access arbitrary data in the database. So as shown in the picture, even though we specify a wrong password and username, we can still leak the correct user data with the craft hidden properties. So here is the last case in this talk. Before we can introduce this case, we would like to give a brief introduction to the event handler scheme of Node.js. So in Node.js, there is only one thread handling all the incoming requests. As a result, the availability of the event handler is really critical. In the third case, we want to demonstrate how HPA can attack the event handler and thus freeze the entire server programs. So in Mongo Express, we found a hidden property which allows us to pass a function definition. This function will be executed in an isolated safe sandbox. Even though we cannot execute the commands using these hidden properties, we can still block the event handler by passing an infinite loop. So as shown in the bottom of the picture, if we pass a hidden property through the web API, which is an infinite loop, then upon receiving the request, the whole site will immediately get blocked. So thanks for attending our talk. This is pretty much about our research. You are also welcome to follow me at Twitter on the bottom of the slides. Thank you. Okay. Hi, everyone. So I'm here to taking questions. Okay, so I noticed that there's already some questions in the chat box, so I'll answer this question first. Okay, so for the Lynx code release plan, so actually we are cleaning up the project and prepare the documentations. As you guys may notice, we have several modules, and from the HCI part, the interface is not so user-friendly. So we are trying our best to prepare the documentations and also clean up the code in case some researchers may want to read our codes. And so that's why our plan is to release it no later than the end of August. So this is the first question. And so for the second question, Is there any paper or blogs from you on this topic? I'm sorry that actually we are only maintaining our internal technical documents, and in short term we haven't had a plan to release it publicly. Yeah, so but we will probably release a complete write-up, a white paper along with the project sometimes. But yeah, but we will give out our source code first. Yeah, and yeah. So as for the Twitter ID question, okay, so I will send you the Twitter link soon. So is there any other questions? Okay. Okay, yeah. So, we're having about 4 minutes. If there's any question, feel free to ask me. Okay, so I noticed there's 2 more questions. Let's take a look. Okay, so for the question from Jason, thanks for the question. So Jason is asking about, does this mean both the expected and unexpected parameters need to be synchronized, or there is a more elegant solution? Okay, so in our research, we mainly focus on the hidden part, which is the unexpected parameters. And we believe that it is actually not we believe that the synchronization is not the silver bullet, because some synchronization or validator modules are also directly vulnerable to our attacks. So we believe a more elegant method is to let programmers, developers to be aware of those hidden properties. So that's why we developed and want to open source our code. Yeah. And it seems that we still have time, so maybe we can take another one question. So the question is, you mentioned that the most traditional payload validation tools are not able to deal with HPA vulnerabilities because they are also vulnerable to it. JOI. Okay, yeah. So I kind of so we test 60 modules. I kind of remember that I choose that one, but unfortunately we didn't find exploitable hidden properties, if I remember correctly. Yes. So I will check if we still have time for taking more questions. Okay, cool. Yeah. So I just share my my Twitter through the chat, and if we are about to release our tools and the white papers, I will also make a tweet about it. Yes. And okay, so if we have time, we can take other questions. Please wait for a moment. It seems okay. Yeah. Okay, so it seems like it's still many questions. So and we don't have that much time. So probably we can. I will take the question through the chat box. Or then yeah. Thanks for all you guys attending my talk. Yes.